Yeah.
Good morning, everybody. Good morning. Hope you're feeling nice and relaxed. We don't have another exam in chemistry for 3 weeks, 2.5 weeks now. Got a little bit of time. And I just want you to keep in mind that every exam in this class is going to be on the final exam. So if you realize that there's some spots maybe you didn't know as well as you thought you did on the exam, and then when you get that back, I'll give them back on Friday. Give the scores out probably later today or tomorrow. Then you should be able to take a look at that, see what you still need to work on, and then show me on the final exam that you know how to do those things. Yeah, Joe?
So are they all graded already?
Nope.
No.
Or else I'd have the grades posted. Haven't gotten there yet. I try to be as efficient as possible.
I think you could have technical difficulties.
Yeah, that does happen.
Kind of didn't work.
So today's class, what I want us thinking about is chemical equations. And maybe to start with, there's a really, really important distinction. What happens in a nuclear reaction? Talk to your neighbor, try to describe what all nuclear reactions have in common, and we're going to contrast that to a chemical reaction, because those are completely separate. The nuclear reaction. Oh, yeah. No.
And
can I hear from the group of Lori, Marlene, or Alyssa? One of you three. What did you guys discuss?
It has to do with the nucleus.
Which does? Which of the two?
The nuclear reaction.
Okay, great. What about the nucleus?
It's changed.
Okay, what's in the nucleus? Electrons? No. So a nuclear reaction is specifically a change. We're going to do delta for change in hashtag protons.
oh god.
Or neutrons, okay? So either it spits out an alpha particle, or it converts a proton to a neutron, or neutron to proton. Those are nuclear reactions. We visited those in the beginning of the semester because I think it is a good time of the year to discuss that. A lot of times it's not done until the end of the year because it's kind of like this off topic. But we were talking about what the nucleus is made of, so that's a good time to talk about when you have changes in those. The rest of the semester in chemistry, we're going to be talking about those kinds of reactions. So, can I hear from another small group, what happens in a chemical reaction? Moed?
Reactants react without changing their initial chemical properties, and they stay as the same elements.
Okay, so I'm going to tease out one thing you said. There's some stuff I'm not quite clear on, but the elements themselves don't change. That's a big difference from over there, right? There we said the nucleus changes. If we change the number of protons, we now have a different element. And when any chemical reaction occurs, that is one thing that does not change. If we start with carbon, we end with carbon. If we start with oxygen, we end with oxygen. The properties, I'm going to argue, that's going overboard. That's stepping a little bit too far. So what is changing in a chemical reaction?
Configuration.
Caleb?
Electrons.
Okay, electrons might be changing.
The rearrangement of electrons.
Okay, so one of the things that can change is electrons can be transferred. So changing the number in each atom, Crush?
Change of state, so it could go from solid to gas.
So that's a physical change, not a chemical change. Lo?
It goes from one molecule to another molecule.
Okay, it goes from one molecule to another. So what happens to those elements, those atoms that are different elements? Matthew?
They're bonded.
So it's a change in arrangement or bonding of atoms. So if we take water and we take it from a liquid to a gas, we boil water. Is that a chemical change?
No.
We're just changing the state, we're changing how far apart those molecules are, but the oxygen is still attached to two hydrogens. That's not a chemical change. So here, what I want us thinking about when we answer this question is, what kind of a change occurs when we burn a sample of ethanol? And actually I was only able to get methanol for our class today, so we'll burn some methanol in class today.
Hey,
So what
stuff.
changes occur with a sample? Let's do a clicker question to start this off. And in order for us to really dig into this, I want you getting in our magic school bus. And we're going to zoom in to the molecular level of combustion reaction. Alright, so picturing the molecules. And just to help us out, I brought a couple of methanol molecules because we're burning methanol. So methanol is CH3OH. That's this molecule, and I brought two of them because I figure that one is a little bit lonely. Alright, so in this magic school bus, we're going to zoom in, and we are going to think about the mass specifically in that sample of ethanol. So it weighs something. I'm going to burn about 10 milliliters of ethanol. So which one of these do you think best describes the mass in that sample as we burn the methanol? And if anyone does not like fire, then you might want to step out of the room for a minute. Mohammed, can you kill the lights for a sec? Thank you. That's good. It's just hard to see this without. Alright, so I poured in a graduated cylinder about 10 milliliters of ethanol. Ethanol has a carbon, 1 oxygen, 4 hydrogens. Think about the molecules. We're looking at the molecules right now. The molecules are doing something. Where is most of the mass of any element found? Protons and neutrons, right? So I want us thinking about what's happening to that mass. Mohammed, do you mind flipping that light back on? Oh, does that? Sorry, that does everything. I didn't know if I had that much control. All right. So we have a disagreement in the answer. Talk to your neighbor. See what you think the best description is of what happened to the mass of those ethanol molecules. Okay, so what's the biggest challenge with the first answer? Can I get a hand raised and you get one voice? Go ahead, John.
Does not follow conservation of mass.
Okay, so conservation of mass means if we had a nucleus there, it's not just going to up and walk away. And then not be there when it walks away. I guess that's a weird way of saying it, okay? So conservation of mass is our rule. We can't just have it disappear. So then can I get someone who wants to argue for one of these two answers? What do we think happened to the mass? Eric?
It up in other molecules with oxygen.
Ended up in other molecules with oxygen. So you're saying that in order for this to burn, we needed something else as well.
Right, because you're releasing it by burning it, which means you're making blue molecules.
So in order for a combustion reaction to happen, we have to combine a fuel source with oxygen. So this reaction wouldn't happen unless we had oxygen. So I brought 3 oxygen molecules. So we have 3 oxygen up here with our 2 methanol molecules. What do we normally form? And write this down, don't bloat this out. What do we normally form in a combustion reaction? What are the normal products that we form in a combustion reaction? Go ahead and write down. If we start with methanol and oxygen, what are we most likely forming? I'll give you a hint. It has all the same atoms that we started with.
What was the formula for methanol used?
There's 1 carbon, CH3, OH. All right, check with your neighbors, see if you guys have similar things. I'm going to do some random calling to hear what the products are from this reaction. All right, can I get 1 product from Kayla? So we have CH3OH plus O2 yields carbon dioxide. Where did this carbon come from? So how many carbon dioxides can we make if we're just looking at the carbon?
1.
Okay. There's only 1 we can make for every methanol molecule. If we had ethanol, it starts with 2 carbons per ethanol. So we could possibly make 2 carbon dioxides if we had enough of the other reagents as well. And then what's the other product that we make? Can I hear from Sam? And where does the hydrogen in water come from? Does it come from the oxygen or from the methanol? All right, we don't have any hydrogens here, so every single one of these hydrogens has to be accounted for on the product side in the form of water. There's no other source of this. Can't get into this equation unless we started with it. So hopefully by working through model 1 of the activity, you kind of started to visualize some of that. I think the most important part of stoichiometry is visualizing what it means and not thinking about it as just math. It's not just accounting. You're saying that if I end up with a carbon over here, there had to be a carbon over here. So if we go back, can I have someone explain why one of these 2 answers is much better than the other? Much more accurate. Diana?
C accounts for everything?
Say again?
C accounts for the products?
Okay, great. So what does that mean that B does not account for?
The everything in it? Like the start products and the end products.
Okay, so you're talking about reactants and products. So B ignores that there has to be oxygen for that reaction to occur. B also doesn't take into consideration that it is a chemical reaction. What would happen if it was B? What type of a change would that be?
Evaporation.
Evaporation, a physical change. So this is true that ethanol can or methanol can evaporate and go from a liquid to a gas. But in this case, you saw light being emitted. A change in color or a change in properties is oftentimes, going back to what Mohib said, a change in properties is very often an indicator that we had a chemical change occur.
We also saw to give off the light from quantum transitions that would require energy to be released.
Rearrangement of atoms to form new bonds. What do you think is more stable? The products of this reaction or the reactants of this reaction? products because it gave off energy in the process of that transition. Needed a little energy to get started. Okay, so that was our little, we can go back, we can balance this equation later. I'm not worried about that right now. That might be something you write down to do later, is to figure out how to balance the equation of the combustion of methanol. But for right now, what I want to start doing is I want to then go into the activity that we did. First thing I want you to do is, if you're not sitting next to someone, please find someone to share your work with. And I want you to talk through the 3 diagrams you have. You were supposed to draw out the products, put circles around the reactants, boxes around the products. Make sure you're all on the same page. So spend about 1 minute doing that. See if there's any differences. Look for differences and try to figure out why. Marky, do you mind scooting over one? Do you mind scooting over and joining Logan? Okay, so we're going one step at a time, making sure that we're all on the same page before we move on to Model 2. So let's talk out a couple things. What does the term reactant mean? Can I get a hand raised, different voices, as much as we can. What does a reactant mean? Grant, I hear you internally raising your hand.
What's the question?
What does this word reactant mean?
That's just whatever is happening before the change.
Okay, great. So I like that you put time into that. You said before. So it's what we start with. So as a reaction progresses, is it there in the end? Okay, there's some subtleties we'll get into in second semester where the answer is yes. But for now, we're saying that a reaction, we assume it goes to completion, which means that everything that started out as a reactant ends up as what? Product, if there's enough of everything. We're going to talk about limiting reagents on Friday. That's what your pre-reading and your pre-quiz is for Friday. There's 2 simulations I've put up online. Remember, if you can't see some of the simulations I put up, make sure you view all assignments, and then it'll show by due date what I've suggested you look at. There's 2 different ways of looking at limiting reagents, so I have those both up Friday. You can do one or both, or neither if you're comfortable with limiting reagents. Okay? So then on the right side, these are all products. This means in time after this reaction is done, this is what we have left. What does this arrow in the middle represent? Say again?
I always thought it was like an equal sign.
An equal sign?
Yeah, so.
Okay, so mathematically, it might be a little bit like an equal sign. Can we answer that?
It can also signify that it's a chemical reaction that's occurring.
So it signifies a process occurring, I think I'd say. Sometimes we can go from different states, and we still have the arrow. So I'm going to go back to Grant's description of time. That this means that this signifies on the left is before, on the right is after. Okay? So when we were doing nuclear chemistry, I had a lot of people drawing arrows to the left. That's not typically the way we do it, just like we read left to right in a book. We're always going to do chemical reactions with the arrow pointing to the right, as much as we can. So try to always make sure your reactants are on the left, you have an arrow, and then you show the products on the right. Any questions about that? Who knows the name of this reaction? Can I get a hand raise? Nice hand raise there. Under my breath. Okay, can you say that louder? All right. You guys have all taken a biology class, right? Yeah. Okay. So, taking carbon dioxide and water, pulling those out of the air, generating glucose or more complex sugars, and releasing oxygen into the air. That's how we get the oxygen we breathe, is photosynthesis. So let's keep that in mind. Go ahead and compare your answers to question 6, how you completed that table. Look for any differences. Be really specific to look for differences. Does everything look similar? Do you have any differences? Okay. And when you're done, go ahead and compare your answers to question 8, which is another table.
For this one, did you want the number of molecules?
12.
Oh, okay.
Okay, so we're going to talk through what you guys looked at for those 2 tables. Table in question number 6. What did you notice about the number of atoms from reactants to products in each of those 3 reactants? So? They're the same. There's no change in them, okay? What about the number of molecules in the reactants versus the number of molecules in the product? Manu? Not the same. So reaction 1, we have 6 carbon dioxides, 6 waters, and then we have 1 glucose and, was it 6 oxygens? So those numbers of molecules don't align. The reason this seems maybe so simple and childish the way that Josh said the answer, right, is because if you look at it this way, it's stupid simple. But a lot of times if you just dive into the math of it, you get stuck and then like, oh, we started this many molecules, we're going to end with this many. It is a very common misconception that happens. And so by looking at it visually, thinking about the molecules, and the numbers just represent the molecules, we can then start to actually do the math with a lot more confidence in understanding what it means. All right, go ahead and compare your answer to question number 10. Feel free to modify yours if you like what other people represent.
They're the same number of atoms.
Couple more seconds. Can I hear from a new voice to volunteer what you think your group kind of came up with for this idea of a balanced equation? What does it really mean? Christina? Same number of each kind of atom on both sides of the equation. Great. Did anyone have something additional to that? We can go even deeper than that if we want. Angel?
But there are not always the same number of molecules.
Great. So we can focus on the number of atoms of each type of element are conserved. The number of molecules don't have to be. There's even one additional layer to that.
Make sure that mass isn't going to be destroyed or anything, so you want to make sure that it's balanced
Great. And I think this is the underlying principle behind what Christina said. That the same number of atoms are on both sides. We know that the atoms aren't being converted, right? These are not nuclear reactions. So that means that all of the mass, all of the nucleuses that you start with are unchanged. All of the nucleuses are there afterwards. So that means that all the mass is there before and after the reaction, that the mass is conserved. So I think for me that's a very important part of a balanced equation. Rhea, did you have an additional comment?
No.
Okay. So what if we look at reaction 1? I want you to discuss what would happen to the amount of products that we could make if we added 6 more CO2 molecules to this reaction. Talk to your neighbor and try to decide what would happen to reaction 1 if we added 6 more of the CO2 reactants. What would happen to the amount of products? Christian, do you mind sharing your group's wording with the class? Christian, do you mind sharing what you described from your group's discussion?
We said that nothing would change because you would need more hydrogen molecules in order to make glucose.
I would just tweak the wording a tiny bit. I would say you would need more hydrogen atoms. Where do we get hydrogen atoms in this reaction? And the reason I was so careful about that is because hydrogen can be a molecule too. So there's certain gases that are diatomic molecules. Hydrogen, oxygen, bromine. There's a whole bunch of other ones that nitrogen. When you have the gas, you just refer to it as the element name, but you say nitrogen molecule, and then you know there's 2 of those atoms in one molecule. I think you'll see that in the homework some this week as well. So if we add more of these, we can't make any more products than are already there because we don't have any more hydrogens and oxygens to combine in order to make what's on the right side of this equation. So then let's get into a little bit of terminology. What is the limiting reagent in this reaction that we just described? Go ahead and talk to your neighbor if you're not quite sure. All right, a couple more seconds. So we have a vast majority of people that are answering B. So in this reaction, we're saying that B is the limiting reagent. Can I get a new voice to describe what limiting reagent means then? Trey?
It would be the, I guess, the side of the molecules that are limiting everything from producing the desired product.
Okay, desired might be a strong word, but the products of the reactant. So to reword what you said or restate it, you said the one that limits how much we can make. Is there something else you guys want to add to that as far as how you think of limiting reagent? There's a number of different ways to describe this. Yes?
The thing that runs out first.
Awesome. I think that's really like just everyday wording type of approach to it. We need 6 and 6. We need 6 for every 6. If we have 12 of one and 6 of the other, we're going to run out of one of them first. So the one we're going to run out in this case is the one that we only have 6 of. And I want you to be really careful that in order to make that decision, we have to think about what the ratio is of the balanced reaction first. It's not just a matter of 1-to-1 always, and we'll see that in a second. Moab?
So, what if we only had 6 molecules of CO2 and 6 molecules of H2O? Which would they both be limiting reagents, or neither?
So in the diagram here, is there a limiting reagent? Nope. It's a good question. We don't call anything a limiting reagent if we consume both of them and there's nothing left over afterwards. But the one that runs out first, if we don't have the exact right proportions, is our limiting reagent. All right, so then let's think about combustion versus photosynthesis. So here now I've shown the combustion version of the reaction. Go ahead and read this question. It should show up in your phones as well on your clicker.
Yes, it is. I'm pretty sure it's molecular biology.
That was a terribly worded first line of the question. Combustion releases energy, photosynthesis requires energy. Not the point of this question, but still a glaring mistake. So go ahead and talk to your neighbor. Try to figure out if you have 3 molecules of glucose reacting with 12 molecules of oxygen, what is your limiting reagent?
Look at the ratio between glucose and oxygen. So if you had 3 glucoses, you would need.
You guys are split 2-to-1. Turn and talk to someone. Find someone who has a different answer than you and try to figure out why and try to convince them that your answer is right if you believe it. Try to find someone with a different opinion, please. Okay, has everyone had their most recent vote submitted? All right. We still have 2 answers. I want you to think about how to put in a sentence really clearly why you decided the answer you do. I want you to think about it for a second, and then I want to hear from someone new. Let's hear from Josh.
If you look at the equation, 1 molecule of glucose reacts with 6 molecules of oxygen. And you have 3 molecules of glucose and only 12 molecules of oxygen, so oxygen will be the limiting reagent.
How do you guys feel about that description? What I want you guys thinking about is a sentence exactly as Josh talked through it. So if we have 1 molecule of glucose, it will require, is the other way of saying it, 6 molecules of oxygen to consume that 1 molecule. If we don't have 6 molecules of oxygen, this reaction just doesn't even happen. Done. Stops. We're talking about moles, it's a little bit different, because remember a mole is a billion, billion, million. So if we have 1 mole of glucose, we can use less than 6 moles of oxygen, because that's 6 billion, billion, million, right? So moles is where students get a little bit confused sometimes and say, well, if I have 1 mole of glucose, I have to have 6 moles of oxygen. No, we just need to think about limiting reagent. So if we have 3 moles of glucose, how many moles of oxygen would we need to consume all 3 moles of glucose? 18. We don't have 18. So that's why I put this particular question up here. The last one was 6 to 6. It's easy to see. It's a 1-to-1 ratio. It's not always a 1-to-1 ratio, so this is a 1 to 6 ratio. So we need to figure out how many we would need to consume the other, and then we can think about how many products we can make. So maybe let me do one more quicker question on this. So in that case, because we don't have 18 oxygen molecules, oxygen is our limiting reagent, right? So just make sure we have this question answered. So then the next question I'm going to ask you guys, it's not written up here, is how many carbon dioxides will we make with these reactants? How many molecules of CO2 will we make with those reactants? Go ahead and click in your answer. Couple more seconds. Go ahead and make sure you have your answer clicked in. All right. Can I have Kyle describe what your group discussed, how you got to an answer?
Yes. Okay. So we have 12. And we got 12 molecules of carbon dioxide
can be produced
by 3 molecules of glucose and 12 molecules of oxygen.
Okay, and why?
And it's because we have the 1 to 6 ratio, so we can use 2 of our glucose and all 12 of our oxygen, and then when we combine those, we get twice as much as we have now, being 12.
Great. So the ratio is 1 to 6 to 6 to 6. So if we use 2, 12, we're going to get 12 and 12. All right, that's one way to look at it. Is there another way that someone looked at this or thought through that they want to share? All right, and we're going to be doing a lot of calculations that'll get to the same thing. Today we're really working on the conceptual side of things so that when you're doing your math, you can actually check to see whether it's right or not. This is one of the parts of the semester where students just dive into the math, get answers that don't make any sense, and move on.
Yes, there's a different way.
You have a different way you want to describe it?
Not really.
Okay.
The way you said it after, it's like dive into math.
All right. Math is still really useful, but it's a way to support the concepts that we want to work on. Okay, so now we're going to go ahead and work on Model 2. Make sure you're working, bouncing ideas off of other people. So try to work through it at a reasonable clip. Try to keep conversation focused on these questions. I think with the framework you have now, you can work through these pretty quickly. If you forgot to bring your packet, it is online, and hopefully the person you're working with you can pair up with to see how they're working through this. 10. Both week 7 and week 8, I put it both.
Be really careful not to.
That is so amazing. Oh my God.
exactly what you'll get now. It's okay.
So let's bring it together for a minute. There's a couple different ways you can answer a question. I think it's, 11? The first one, whatever the first question is. You can either answer it by finding the molar mass. We're going to be using the molar mass a lot. So in the case of carbon monoxide, what is the molar mass? What'd you guys find? 28.0104. And the units of that are grams per molar, the units that are most appropriate to use because we have masses in grams. We could also use the units of AMU per molecule. It's how heavy, in either grams or AMU, the quantity is, a mole or a molecule. So the thing I saw some other people do, which I think is great, is they also said, well, this is really a dimensional analysis problem. The question says, 1 mole of carbon monoxide, how heavy is that? So what conversion factor do we have to go from how many in moles to how heavy in grams? The molar mass is our conversion factor we want to use. So we know that if we have 1 mole of CO, that weighs 28.0104 grams. And so in this case, we find what's really intuitive and really obvious, that 1 mole of those molecules weighs 28.014 grams. But the point is, we're not always going to have 1 mole. They gave us 1 mole in this question, right? But if this was 7.352, this is going to help us really quickly establish that if 1 mole weighs 28 grams, then 7.8234 weighs the same proportion. It's going to weigh about 7 times as much. All right? So we can do the same thing for part B. And then where do we go from there? Can I see this for a sec? So what is the total mass of our products? How do we figure that out? Joey? You add up the mass of everything we started with. So the one thing that we forget is that if you start out with 50 grams of something and we do a chemical reaction, we still have 50 grams of something in the end. It's just different somethings. They might be arranged in different places. It might be that we didn't use up all the reactants. Well, you had a limiting reactant and we had an excess reactant. But those are still going to be the same weight before and afterwards. It's just some of them are going to be rearranged. And then how, for part D, did you guys determine the weight of the products individually? How do we do that? Well, we can determine the molar masses of them individually, but how much mass, how many grams did we make of each one?
Well, the reactant masses, the moles, and we determine the amount of moles of the products, and then from that number, convert the moles back to mass.
Great, so if we look at how many, we started with 28.0 grams of carbon monoxide, is that right? And it was a balanced equation. Remind me the equation. It was CO plus H2O yields. Okay? So if we have 28.0 H2, 28.0 grams of CO, we can find how many moles by using the molar mass. 28.0104. Is that what it was? Grams of CO is 1 mole of CO. And then if I want to determine how many moles of product, for every 1 mole of CO I use, how many moles of CO2 am I going to produce? 1 mole of CO yields 1 mole of CO2. Is that always going to be true?
No.
Remember some of the other reactions? It was a 1 to 6 or a 1 to 3 or whatever the different ratios are. This is one of the most important things we're going to do today. This right here is using a chemical equation the way that Josh said it in words, and it puts it into a conversion factor. This is a new conversion factor we have because of a balanced equation. After we're done with this, we now know how many moles of product of that one product we're going to form. So then how do we go from the moles of the product to how much it weighs in grams? 1 mole of CO2 weighs how much? Okay, this is why we learn dimensional analysis. So we have 3 steps to find one mass of one product. Friday's homework, the pre-class quiz, is going to ask you to do this and think about which one is limiting and which one is not. Make sure you don't compare mass to mass, you compare how many moles of each, look at the molar ratio. You'll get some practice on that, and the homework's up for Sunday. I have modified office hours this week, so please check Blackboard to see when those are. I don't have office hours Friday.